All right, let me just test out one or two things here. We'll see if this is. And we are back. So, what we've got tonight is a little bit different. What we're going to do is we're going to create a uh, a lunch and learn slideshow. Um, essentially, what I'm going to do is I'm going to take everything we've talked about, um, for the past couple weeks, and I'm going to make it into a slideshow to present at my office. So hopefully, this will serve as a good recap of sort of what I've been working on, and sort of get the some coworkers up to speed on best practices with topology optimization, or well, maybe not best practices, but at least what I've learned. So, gonna get some sound running. Have your own soundtrack if you want. I just can't stream, otherwise I'll get copyright struck. And let's dig in. So to begin, we're gonna sort of go over the outline, and then I'm gonna have to start generating some additional content for the meeting, and that will be tonight. So in general, uh, this outline slide is less useful now that I look at it. Okay, so what is topology optimization? So, can I set this to autoplay? Not, not really. Oh well. If I click off it, it stops. Wow. Interesting. Okay, that's better. Anyway, topology optimization. It's a simulation method that optimizes the amount of material and design for a given set of loads and constraints. So you can see here they've applied some loads which we can't really see at this point, and then they've added regions that you have to keep. Looks like some bearing surfaces here, here, and then based on those loads, the algorithm decides what parts you really need to keep. Zoop. I'll just get out of the way. So there's a few other ways to optimize designs, and I'd like to just touch on them real quickly, if only to highlight the differences. So sometimes you'll hear about generative design, and that's a little bit different. So topology optimization takes a design space. So like you saw in the previous slide, you start with a lot of material, like all the available material, your entire space claim, and then you add your constraints, you add your loads, you add your regions to keep, all that sort of stuff, and then you whittle it down by a percentage or an amount or a specific target, and then what you have left is sort of the optimum. Generative design starts the other way. So instead of having like a block with a hole in it, you start with just a hole, which is a little bit weird. But so you could have like a bolt pattern that you need connected, or some sort of bracket where you just know I want this surface and I want this surface, but I don't really know how I want to connect them. And then you apply loads. and it sort of like grows the geometry instead of whittling away. It grows it like a tree. Pros and cons. I don't have access to a generative design software package, so we're stuck with topology optimization for the moment. Then sort of like an older school version would be parametric or sometimes shape optimization. So what you would do is you would create your model, your best guess, and you'd have a bunch of parameters driving like feature size, placement, load placement, that sort of stuff. And you would define like a range and an increment for each variable that you want to check. And then what the algorithm will do is it will go and sort of explore the space. If you're familiar with like design of experiments, this is just a brute force method where it just tries every possible combination of those variables, and then it will simulate every single one of those scenarios, and then you can just pick the best one. You want like a certain strength to weight ratio, you want some sort of heat transfer ratio. That's all possible. It's also very, very general. So there aren't as many ways to run a topology optimization study or generative design study as there are like a parametric or shape optimization. Pretty much, since it's so brute force, this is very, very general. So like a lot of like more niche simulations like E&M type stuff is almost always going to be parametric shape optimization, just by nature of I don't think anyone's written that software for or yet anyway. So one thing I've seen is well, why don't you just like run a normal structural FEA and remove the areas of flow stress? Well, there's some boring math that we could do to explain why areas of low stress contribute to stiffness. But it's a lot of matrices, and it's gonna not be super interesting to go through. So I decided we'll just come up with a little example here. So this is for entertainment purposes only. It ignores almost all best practices for design, simulation, and manufacturing. I don't condone this approach, and we'll try to do better on the real deal. So let's say you have a bracket. This is the dumbest bracket. It's really just a beam. It's just a beam and bending. So it's 135 grams. You've got 100 Newton load, and it deflects by 5.6 times 10 to the negative third millimeters. It doesn't deflect. Now, so here's your stress distribution. Here's your deflection map target. We're going to target like a 70% reduction in mass and still keep the deflection under 0.1 millimeters. So let's look at a stress-based material removal. So here's sort of that chart we looked at before. So we did an iso clipping of all the areas of lowest stress and just cut those away, right? Low stress, that must not be doing anything, right? So we got down to 92 grams, and it is deflecting by 0.027 millimeters, which is, you know, an order of magnitude worse than what we were seeing on the other one. I didn't push it any further than this to try to get to the 70% because it starts getting really wacky. Now, obviously, this is a bad approach. Anyone with a half decent understanding of load pathing could do a much better job. I'm sure you've all seen bridges. This is a bridge. It's a cantilevered beam problem. This is very well understood. And this is the worst way. This is a terrible way to try to solve that problem. An intuitive approach is almost certainly going to be better. Now what we look at is the topology based topology optimization based approach. So you start to see a lot of familiar triangles here. You start to see sort of that load pathing that you would expect to see sort of from here down, and you can see that it would have preferred to keep that angle going in the design spaces. Maybe suboptimal. Maybe if you had some freedom, you could expand this design space down, get maybe even better stiffness to weight ratios. But anyway, we see here that if we take this result and then sort of create geometry based on that, what we see is a mass of about 41 grams. So that's a little better. That's a little better than the 70% reduction we were shooting for, and a max deflection of 0.18 millimeters. So it's half the mass of the previous approach and less deflection. Now, this is a silly example, but it sort of gives you a really rough idea of the workflow and what's capable. And now, while this is a really simple case, you can easily imagine a load case or a geometry where the load pathing is less clear, not as easy to understand, or maybe you have multiple load cases. So say you needed to like load it in like 3 or 4 different directions or at several different points. The contribution of each load is not going to be as clear, and the combination won't be either. So let's jump into one of those cases. So quadcopters, those are cool, right? So weight and stiffness are critical. Just like it has to be light to fly, and if it's not stiff, you get some weird resonance stuff, and it doesn't fly very well. So sort of the overall size and the number of features and the size of those features make it a good candidate for 3D printing, which is nice because that means we don't have to really think about making this optimized design manufacturable at all. You can just let the algorithm run wild and ignore all DFM considerations, at least most of them. So, constraints on this problem, we're shooting for a total weight, battery included, under 250 grams. That's driven by a certain class of FAA regulations for sort of like UAV type stuff. The frame size, we're going to try to keep that under 3 or at 3 inches, which is a standard size, and it easily fits in the build volume of some really cheap SLA printers. Then we start getting into loading stuff. So the higher the thrust to weight ratio, the better. You really need at least 4:1 to do like acrobatic flying, which is the goal for here. And then like top end performance would be closer to like 10:1. So then we can just back out some loads from that. So load cases. So we're going to have a quick aside here for quadcopter flight dynamics. With a quadcopter, it has all the degrees of freedom, right? So you've got pitch, roll, and yaw. So pitch and roll are pretty easy to conceptualize. If you want to roll to the left, you just increase the thrust on the right side and decrease the thrust on the left side, and you will roll to the left. And then pitch, likewise, increase on the front, decrease on the back. You're gonna pitch up. Now yaw is a little bit weirder. So the way you do that is um, you will like so the motors spin sort of in pairs. So there's two that spin one direction and two that spin the other direction. So the way you yaw is you slow down one pair of motors and you speed up the other. And due to conservation of angular momentum, the quadcopter itself spins. Um, so this has all sorts of implications for the size of motor you want and a couple other ratios that we won't go into that control. It's called yaw authority, but that doesn't factor into our calculations at the moment because that's sort of out of the realm of control of frame design. So we're just gonna look at the forces that will likely be involved. So obviously you have thrust forces, and that's purely vertical on each of these four motor mounting points. But then as you're spinning the propeller, it has a reaction force. So it creates a thrust, then you need to counteract that torque. So like if you took the tail off of a helicopter, it would just spin around, right? So you need, there's a reaction force there. So we can estimate that from propeller data sheets. So we pulled that and we're estimating about 16 newtons of thrust to 17 newton meters torque. Seems ballpark right, and we're just going to plug that in and see how it goes. So setting up the simulation. Let me see. This slide might not be good. We might juggle this a little bit. Yeah, this slide isn't good. We're gonna make that redundant. Okay, so we're just gonna jump right into load cases. Uh, Load cases, fixtures, optimization goals. So instead of having a summary slide and then going into details, I think it's better just to jump straight into the details, at least at this level. So we're just going to break a little bit about that out here. Ooh. Yeah. One moment, gotta check something out real quick. I will be right back. And we're back. Sorry about that. So where were we? All right, we just load cases, load case manager. All right, actual loads. Now, SolidWorks glitched out. And here we go again. Let's. Okay. Keep getting pulled out, but we're back. So SolidWorks crashed and deleted all my studies here, so we are starting from scratch again, but that's okay, because now I get to double check all my results. So we're going to do topology study, and we got the ABS, there's no contacts, fixtures. All right, how did we do this? Geez. Let's see if I have anything. Was I kind? Future me? No, of course not. All right, we're gonna just have to think about this a little bit. So these faces are gonna need to be constrained, yeah? So we have this whole geometry controlled. So I think the way we're gonna think about this is the stack staying stationary and the arms waving in the breeze. Symmetry plane. And now we're going to apply some loads. I think the second way I did this was relatively intelligent. I had some pictures of that. Please. Okay. It's not quite brain dead. Yeah, let's do it. Now, let's make this a little bit more distinct. Can I get like some sort of... No, I guess not. Results advisor, okay. So I'm trying to find some way to get this to display this intelligently, but it's just not. So we're gonna have to do it ourselves. It's fine. Yeah. All right. So now, what we can do is we can grab this and we can change the color. We're going to snag this lovely shade of green. Actually, scratch that. Blue. Why? Why would it do this? All right, and we're going to do the same here. And we're going to grab this here. Yeah, all right. So now should be able to see what these mean. Okay, it's not the best, but we'll work with this. Let's skip for that. And back to loads. All right, so external loads. So we're going to put force here, here. We come back to our slides, and we're going to say 15.7 newtons of thrust. So that's 15.7 newtons per item. Down, check. Let's see. That will always be down, right? How could it be up? It is extremely unlikely that it will be up. We're not doing 3D maneuvers. What are we gonna call it? Okay, this is what we want. Copy image. Boop. I don't know if that's actually useful, but I am taking it. What? Wait, I'm not putting the reversed in as default. Even, there we go. Copy. There it is. That was almost pretty troll. All right, here we are. So we got the thrust load. So now we're going to apply torque. And here's your axis. I think that was like 16.7. 16.97, so 17. And okay. Oh, right, okay. So thrust and it's gonna be motor 4. Yeah, we can control direction. So we set nominal direction, and then we control everything else as signs. So we're gonna come in some multiple load cases. Torque here. And we want that to be is that correct? Yes, those are correct. So these are both set for the nominal forward direction. Now we come in, well, now we come in and get some pictures. So we're gonna hide that, and come in and hide these. Show this one. Can we alter Yeah. Okay, now you might remember from earlier that we were talking about having much higher loads than this on the thrust to weight ratio discussion. However, at this point, what matters more is the ratio, because this is just going to tell you what your best design is for stiffness. It won't necessarily tell you if your design's going to actually be able to do it. It's just going to say, well, this is your best shot, boss, but it's not going to tell you if you're actually going to succeed. That is another discussion entirely. So let's do that same thing. We're going to come in here and we're going to change these colors a little bit. We're going to make these orange. Increase that size a little bit so you can actually see it. Yeah. Same drill. Thrust. Grab this lovely color. Apply. Zoop. And torque. Copy clipboard. And there we go. Now, some more tedious load manager stuff. Call this thrust. And this is going to have the full thrust load. We're going to do torque forward. And that's going to have both of these at their nominal. And then we're going to do torque reverse. So this is same deal, but we're just going to come in and alter the signs on both of these. There. So you can see in there we got just a reversed situation. So we're gonna grab a little better screenshot than we did before here. And we're gonna grab the whole screen and toss that in our records, but not the slideshow. particularly interested in what that says right now. So now we're going to do, let's see, fixtures, loads, optimization goals, and we're going to toss manufacturing. Okay, so we can see here it's currently 300 grams just for um, uh, the half we've got here. So I think we looked at some COTS frames, figured that about 30 grams was where we want to be, and uh, so that calculates to 15 per side. And whenever you increase or whenever you make these things parameterized, you never get quite as clean of a cut as when you do with the STL. So what we need to do is we need to reduce this by an amount to get probably 10 grams per side. So probably 298. Yeah. So that puts our final mass around 10 grams. And the stiffness, we're not going to leave a frequency constraint in here. Because like we don't care about the resonant frequency of the frame as much as we do the resonant frequency of the system, and we can't simulate that right now in this study. So that's not really gonna help us. So let's grab a screenshot. That slide ended up not turning into manufacturing constraints. Just gotta generate the content first, then we can worry about sort of the appearance. All right, so we've got our goals. Now we're going to add our preserved regions. So what this does is tells the algorithm, hey, I need this bit, don't get rid of this part. So this is important, otherwise it will just sort of get rid of everything, you know? And that's not helpful. Okay, this is, should this be here? That's a little whack. Oh, right. I think we're gonna set that to like 4 millimeters. The minimum sort of feature size that we can reliably get on an SLA printer, I believe, is somewhere in the neighborhood of 3 to 4 millimeters. So that's sort of what's driving that wall thickness. There we go. There's our screenshot there. And then we're going to add a general thickness control here. And we're going to make that 4 millimeters again. That is such a weird way to represent that. See how's our mesh doing? We'll accept the default for now. It should just take a couple seconds. Yeah, there it is. Does it seem reasonable? It's not terrible. Should probably put something in here about the space claim. We'll get there. We will get there. I think that's it. So we're gonna run the study, and then while we're running the study, we'll dig through some part selection because there's been some neat stuff in the past couple months. And I have not kept up with it. The study failed. Interesting. Okay, that Doesn't happen a lot. Why though? Does it say why? Let's close this guy out. So we know the mesh is good. Let's just start suppressing things sequentially and see. Oh, static solvent failed. Let's try suppressing loads until something works. It's not a good beep. Oh, okay. We didn't do. Can't believe. All right. Wow. Wow. Noob. Noob move. So what you gotta do is this. I think it's this one. Min-max formulation. You gotta. I swear there's an option that I'm not checking here. Convergence check. Right. Okay. Okay, don't do this. Pull that up again. Okay, so there's two things we got to do here. And those are, grab the screenshot, use min-max formulation, and this is for the multiple load cases, and this, so it doesn't decide to just randomly preserve places you apply loads. Super troll. Can't believe I forgot that. I mean, it's good through an error, otherwise it could have run for like 45 minutes and then given me who knows what kind of junk. And then you come into advanced. How did whole thing? Yep, advanced. Yeah, there it is. Oh, that's not right. There, max. Properties, check. And there. I'll add some text while it's running, but that should do it. All right, let's run this. We're gonna let it get to like, okay. Still something wrong. What? What am I doing wrong? The static study is not working. Interesting. Well, this is live and uncut. Where am I being an idiot here? So the symmetry, I mean, it's good, it's good. So it's failing before it gets to any of this. Let's just try suppressing symmetry load. Symmetry constraint, rather. That doesn't make any sense, but topology study 1 failed. It's possible? That'd weird me out. I mean, SolidWorks has done weirder things though, so like maybe that's it. Latest working theory, I pushed the mass reduction too far, and it's just not capable. Oh, we made it 1%. All right, that is. We have possibilities here. We have possibilities. Okay, so you know what? We are going to take this 5 minutes to make some hot chocolate, stretch out the hands. I will see you back here in 2-3 minutes. Be right back. All right, we are back. Solver is not quite done. That's okay. We are gonna wait it out. So what we got is a good opportunity to go through and add some text to all these random slides. I'm going to shrink these a little bit. A little more room for text. Oh, it's done. Yeah, okay. So, I mean, this is about what we'd expect. It's just the thrust loading, no torque, and only reducing the mass by 9%. So what this tells us is reducing it by 96% is not possible. That's fine. So what we're gonna do is we're gonna do sort of an iterative solution here. So one thing that I've been struggling with conceptually is what to do with sort of the lid over. Ah, jeez. I think hot chocolate water's done. Gonna run and get that real quick. All right, we're back, and hot chocolate has been acquired. So let's get back to it here. Uh, Still at 4%. So yeah, I restarted the study off cam. We're taking it to 75%, and then we're just gonna have to do some sort of manual sort of optimization thing. It's not ideal. We're gonna have to make some cuts uh, ourselves without the algorithm. Um, that's fine, as long as we're not too crazy about it. Um, as long as we can get to the point where we can solve it, fine. Oh, maybe actually, you know what? Actually, we are gonna jump in here and we're gonna try out that draft mode. Oh, I forgot. It takes time just to cancel. All right. Mass properties. Interesting. Hmm. Da. Simulation evaluator. Ooh. Properties. We're going to come in here and do a convergence check only. This is going to be hopefully a little faster, fingers crossed, and that should give us a ballpark. I don't know how much faster it's going to be. It just says faster. Each iteration, the solver checks if the objective or the constraint has converged to the solution. The numerical tolerances between subsequent iterations for reaching convergence are relaxed. If by default the solver uses a smaller numerical tolerance and both the objective and constraints need to be satisfied for the solver to stop. Hmm. We'll see if it's actually faster, or if it even gives a close result. Um, Never tried it before. Yeah, yeah. Oh no, basic math. Oh, hang on. And right? Okay, so if you have 100 grams and you want 90% reduction, it's 10 grams. Nope, I'm an idiot. Well, how are we doing here? Been running. So this is going to take an hour? That's not that's not faster. Yeah, yeah, see. So I think that's where we were running into problems. Okay, so 30 grams. Uh, all right. Let's run through it from. Requirements, load cases, load case manager, space claim. This should go in the space claim thing. Oh, there it is. Dang. All right, so that was pretty quick. That was about 10 minutes. So this is giving us an estimated mass of 78 grams. Let's, uh, there's got to be it's a continuous discrete fringe. Well, that's not helpful. I am curious about that option though. Huh. It's actually that looks better. Soup. Oh, that's nice. See the yeah. Okay. I see why the default is discrete. Seems to line up a little better. Still though, basically we need to get rid of a huge amount of mass. So we're gonna we're gonna get rid of these because it's just lame. All right, so boot boot, and we can see that in another view, right? Oh no! Oh no no no! Damn it! Oh, okay. That's why you don't do that. Okay, it's been a while since I've done this, and we're learning all sorts of stuff over again. All right, pull back and add some cuts here. So we're getting rid of this material that we know we don't need. Um, and what this lets us do is decrease the weight of our space claim to get closer to that target of 115, or 150, sorry. Okay, so this should take like another 10 minutes. Oh, where'd it go? Go back. Let's look at our system performance here. Just curious. Absolutely no load on the GPU. Anyway, back. Oh, that's fascinating. I wonder if I should do that. Huh. I should have read that checkbox. Seems to be used specifically for objects in flight. And gosh dang, this is an object in flight, so I'm gonna click that checkbox. Inertia relief right there. And we're gonna get rid of this fixed. Um, gonna end up with more graphics to replace, but at least we have placeholders, so that's useful. Um, All right, everything else should be fine. Keep in mind, we're still running this with, dang it. But I did the thing. Unbalanced external loading. Do I need that? Unbalanced external loads. If this works, I will be so confused. Okay, so it makes sense why inertial loading didn't work, because like the forces are like significantly unbalanced. So it's not meant to handle that. But it makes zero sense to me why it's working without a fully constrained model or the inertial loads or soft springs. This shouldn't work. I'm not buying it. I'm not buying this explanation. The symmetry loading, shouldn't be enough to fix this. Okay, so what I'm thinking is what we let's see. Did we get anything useful? Just thinking. I mean, it's wrong, but it was only like halfway done. It's kind of whack though. Okay, so we're gonna change how we do this a little bit. We're gonna a lot of it actually. We're gonna head back over here to the model, and we're going to get rid of the entire concept of symmetry here, and hope that by getting rid of the other fixture, we can do inertial relief actually. So there's our mass reduction. Suppress the symmetry constraint. And we're going to come in and re-enable inertial relief. And we're just going to take one last look here to make sure that these other ones are interesting. In plane loading. We'll pass on that. We're done here. Okay. Automatic solver selection. Wait, we want Intel Direct Sparse is perfectly fine. Okay, yeah. We're gonna come in here and just make this go a little faster. Yeah, I know. We're just gonna delete that so it doesn't throw errors. It's gonna mesh. Okay. Static solver failed. I mean, obviously, if I unsuppress this, everything will be fine, right? Okay. I guess I don't understand. Oh, you know what? You know what? Let's try. So instead of suppressing, let's try deleting because it seems to not actually care that things are suppressed. Um, so no fixtures at all. And then we're gonna use inertia relief, and we're actually gonna come in here, and we're gonna add a couple more faces. Um, Static solver failed. You know what? Let's just create a new statics study, and we're gonna just toss torque, or sorry, we're gonna toss inertia relief. That should be it. Toss force load of what? 10 newtons each. Boom. Now let's run this one. Okay. Significant. So this is probably what it's throwing. It's just not telling me. Significant external imbalanced force in the y direction. Yes, I would like to continue. Okay, so inertia relief works in this instance, but it doesn't work here. So these only take a couple seconds to create. So we're just gonna, so this is the exact same setup, right? It's got inertia relief, no soft springs, torque, single load case. Run. So this should be identical to the previous case. The only difference is we're using a multiple load case here, but we're not. Dang, there it is. All right. Why would that be the case? Okay, it's not in the first page of Google. Answer probably doesn't exist. We are in uncharted territory. There's no hope. We're flying by the seat of our pants here. It does move pretty quick though. Makes for an absolutely riveting stream watching the topology study run. You know what? I think I'm gonna call it now. It's just about 2 hours even. This is fascinating, but I've been clicking things for 12 hours, 13 hours today. I'm gonna call it. Anyway, hopefully by the next time we do this, I should have a better understanding of inertial relief. Maybe we'll even pull a SolidWorks vendor into this. Anyway, have a good evening. I'll see you all later.